Hello everyone. Today we're going to talk about Lewis dot structures. So when nonmetals combine with other nonmetals, they share their valence electrons. Unlike ionic bonds in which electrons are taken and ions form, in the sharing interaction we form something called a covalent bond. The valence electrons in the covalent bond belong to both atoms, allowing both atoms to get their octet through this sharing interaction. When atoms share, the result is a covalent compound. In covalent compounds, the fundamental unit is the molecule. The molecule is a group of atoms that are covalently linked together. Unlike ionic compounds, where the smallest unit is called the formula unit, and this is simply where the charges of the anions and cations balance out. In ionic compounds, the ions exist in a large lattice, whereas in covalent compounds, they just exist as discrete small units. The number of covalent bonds that an atom will form equals the number of electrons necessary to complete its octet. So depending on what group in the periodic table an atom is, it will have to gain or lose electrons to reach an octet. The use of electron dot symbols was first developed by Lewis to show how atoms share their electrons in a covalent bond. These electron dot symbols are used to construct what we call Lewis dot structures. Lewis dot structures consist of the element symbol plus a dot representing each valence electron. If we take a look at the example of methane, which has the formula CH4, we can see the central carbon has 4 valence electrons. We can look on the periodic table and see that carbon is in group 4A. The group number is the number of valence electrons that atom possesses. Carbon has 4. If we look at hydrogen, we can see that hydrogen is in group 1A, meaning it has 1 valence electron. Each atom brings electrons to the party, as it were. Each hydrogen brings 1 electron. Each carbon brings 4. The carbon needs 8 valence electrons to be stable. Each hydrogen actually only needs 2. We call this a duo. So when they share, the carbon gets its 8 and each hydrogen gets its 2. We write the final Lewis dot structure as a carbon in the middle connected to 4 hydrogens by lines that represent the bonds. This bond is called a bonding pair because it is made up of 2 electrons. As we can see in the example with chlorine, each chlorine has 7 valence electrons, meaning it needs 1 more to have its full octet. So 2 chlorine atoms can come together and share 2 electrons. As we see at the beginning, each chlorine has a single electron that's unpaired. Then when they come together, we have our bonding pair. The bonding pair is what forms the covalent bond. Chlorine also possesses what we call lone pair electrons. These are electrons that are not involved in bonding. Each chlorine in Cl2 has 3 lone pairs, or what we sometimes call 3 non-bonding pairs. Let's draw the Lewis dot structure for a hydrogen atom. If we take a look at our periodic table, we'll see that hydrogen is in group 1, meaning it has 1 valence electron. So we start by writing out the symbol for hydrogen, which is just an H. We know it has 1 valence electron, so we give it 1 dot. And this Lewis dot structure shows the structure of a single hydrogen atom by itself. Now we know that in nature, hydrogen never just shows up as hydrogen by itself. It always shows up as H2. And in a little bit, we'll talk about why. Now let's draw the Lewis dot structure for carbon. Carbon, symbol is C, is in group 4A, meaning it has 4 dots. 1, 2, 3, 4. Each of these dots represents one of its valence electrons. It's quite easy to see why carbon usually forms 4 bonds, because it needs 4 more electrons. Let's look at the Lewis dot structure for neon. Neon's a noble gas. Noble gases are stable because they have 8 valence electrons and they reside in group 8A. So if we take a look, we write the symbol for neon, Ne, and then we write its electrons. We start with 1 electron on each side. We don't pair our electrons until we've put 1 on each side. So we've put our first 4. Now we put our 5th, our 6th, our 7th, and our 8th. And this is the Lewis dot structure for neon, and you can see it has a complete octet, all 8 electrons. Let's take a look at the Lewis dot structure for hydrogen gas, H2. We already know that the Lewis dot structure for hydrogen on its own is just a hydrogen with 1 electron. Now, if we have 2 of these, we can make an H2. And we have 2 hydrogens with a bonding pair between them. Quite often we draw it as 2 dots, but this can become very messy when you have large atoms. So the better way to draw it is just hydrogen, line, hydrogen. The line represents 2 electrons, and the line is a bond. A bond is made up of 2 electrons. Hydrogen and helium want a duo, not an octet. This makes them special. And the primary reason they want a duo instead of an octet is they are in the first period. And elements in the first period simply do not have the space to support an octet. All other elements in the main group want an octet. So hydrogen and helium are exceptions to the general rule. Let's draw the Lewis dot structure of hydrogen chloride. So we start by drawing hydrogen, and we're going to draw chlorine here. We want to draw them right next to each other. We only have 2 atoms, so we know they're going to be next to each other in our Lewis dot structure. The next thing we need to look at is how many electrons do we have to work with. In other words, between the 2 atoms we have drawn, how many valence electrons are there? If we look at the periodic table, hydrogen is in group 1A, and chlorine is in group 7A, meaning we have 8 valence electrons to work with. So we're going to start by using 2 of our electrons to draw a bond between hydrogen and chlorine. Hydrogen now has its duo satisfied. This leaves us 6 electrons to satisfy chlorine's octet. And we can use those 6 to put an octet around chlorine. So carbon must form 4 covalent bonds to complete its octet. It can form single bonds, or double bonds, or even triple bonds. And multiple bonds are seen in many different compounds. Multiple bonds are ways for atoms to share more than 2 electrons between them. So for example, when we have a carbon with a single bond, carbon shares electrons with 4 other atoms. When we have a carbon with a double bond, carbon can be sharing electrons with 3 other atoms in the case of 1 double bond and 2 single bonds, or just 2 other atoms in the case of 2 double bonds. Carbon also will sometimes form triple bonds, where it shares electrons with 2 other atoms. So let's take a look at the Lewis dot structure of O2. This is oxygen gas. Oxygen gas has a double bond in it. And we know oxygen is in group 6A, so each oxygen needs to form 2 bonds in order to complete its octet. We're working with a total of 12 electrons. Each hydrogen starts with 6 because it's in group 6A. 6 times 2 is 12, so we're working with 12 electrons. We're going to start by writing two oxygens right next to each other. We know already that each one needs to have at least two bonds to complete its octet. So 1, 2. We know this because oxygen has 6 electrons, it needs 8, so it needs to share a total of 4. We've used 4 of our electrons. Now we have to finish our octet. We can use our remaining electrons to finish the octets on the oxygens. So if we take a look at this, we see that this oxygen has the 4 electrons in the bond and the 2 lone pairs that it can consider its own. So on this side we have our 8 electrons. It has its octet complete. If we go to the other side, this oxygen has its 2 lone pairs and its 4 electrons it shares, its 2 bonding pairs, so this side has its octet complete. Everyone has their octet complete. That means O2 is stable and this is the proper Lewis dot structure. We need to remember that the number of covalent bonds that an atom will form equals the number of electrons necessary to complete its octet. And we saw this in O2. Each oxygen needs 2 more electrons, so it forms 2 bonds. And those 2 bonds exist between the 2 oxygen atoms. Let's take a look at N2. N2 is nitrogen gas, and it's the primary component that makes up our atmosphere. Nitrogen is in group 5A, so we have a total of 10 electrons to work with, 2 from each nitrogen. So if we go, we're going to write our 2 nitrogens right next to each other. There's our 2 nitrogens right next to each other. Each nitrogen needs 3 electrons to satisfy it, 3 additional electrons to satisfy its octet. So each one will make 3 bonds. So we're going to make 1, 2, 3. We've used 6 of our electrons at this point. We have 3 bonding pairs. That leaves us with 4 electrons left to use. And the good news is each nitrogen only needs 2 more electrons. So we fill those in, here and here. The nitrogen here has 6 electrons it's sharing with the neighboring nitrogen and 2 that are its own, meaning it has its octet, and the nitrogen on this side has 6 that it's sharing with this nitrogen and 2 that are its own, so it has its octet. We do need to remember to keep track of how many valence electrons we have to work with. Sometimes we'll be tempted to use more electrons than we actually have. A good way to check this is after you finish your Lewis dot structure is to count how many electrons you have used, and then compare that to the number of valence electrons the atoms that make up the compound have. Let's talk about the Lewis dot structure of H2O. I'd like you all to take a moment to try to draw the Lewis dot structure of H2O on your own. If you need to, please just pause the video briefly. Okay, we're back. I'm assuming all of you have taken an opportunity to try to draw the Lewis dot structure of H2O. Now, let's see what the right answer is. Oxygen has a total of 6 valence electrons. Each hydrogen has 1 valence electron. This gives a total of 8 valence electrons to work with. We put oxygen in the middle because it can form the most bonds, and it's also what we call the most electronegative element. We'll talk more about electronegativity later. Draw a large O for oxygen, and we just place our hydrogens on either side. We want to generally spread our hydrogens as far apart from each other as possible. We now connect each with a bond. Okay, we've connected them with our bonds. We've used 4 of our 8 electrons. Oxygen doesn't have its octet, but each of the hydrogens has its duo. But we can reuse our remaining 4 electrons to complete the octet on oxygen. So here's the Lewis dot structure of H2O that many of you may have drawn. We'll talk more later about how we should orientate the atoms and the lone pairs in our second video. Let's take a moment and draw the Lewis dot structure for NH3. If you need to pause the video, that's fine. Okay, we're back. Let's take a look at NH3. NH3 has 1 nitrogen, which has 5 valence electrons, and 3 hydrogens, each of which have 1. This gives us a total of 8 valence electrons. Once again, we'll put nitrogen in the middle because it can form the most bonds and is also the most electronegative element. We put our nitrogen in the middle, and we're going to spread our hydrogens out. We want to spread our hydrogens out around the nitrogen. Now, many of you may have spread it out evenly. I didn't because I've drawn Lewis dot structure for this several times, and you'll see why I didn't in a second. We get a bond between each nitrogen and hydrogen. We use a total of 6 electrons. Our hydrogens all have their duo satisfied, but our nitrogen still needs 2 more electrons, and it gets those in the way of a lone pair. The last subject we'll briefly talk about are formulas and the structure of covalent compounds. The molecular formula for a covalent compound identifies all the components of the molecule, and it is the true formula. Glucose, for example, has a formula of C6H12O6, and this tells us exactly how many carbons, hydrogens, and oxygens there are. In this case, we have 6 carbons, 12 hydrogens, and 6 oxygens. And we'll be using those electron dot structures to help us look at the 3-dimensional shapes of molecules next.